All right, let's get started. So welcome to the last lecture of these courses. So in the last lecture, we started the topics about dynamic programming. Like we have introduced the basic ideas behind the dynamic programming. And we have walked you through this, applying this idea of dynamic programming to solve several problems. Started with simplest one, which is the longest increase in subsequences. We also applying dynamic programming to solve price collection. We also kind of finish the majority topic of the vertex cover on the trees. And let's start from this topic and continue with what we have left it in the last structure. All right. So now, like we already have like the introduction about the problem itself. It is vertex cover on the trees. So the input would be like undirected, unweighted trees, and we also specify the root of the trees. And the output would be the size of the minimum vertex covers. Here, vertex cover means the set of nodes that on the graph, so that each edge is adjacent to each of the node, at least one node in the vertex cover. Right? We are trying to, in these cases, we are trying to output the size of the minimum vertex cover. Then we have two examples as shown in the slides. You see, like for this graph, we have this root as the vertex cover. Then each edge is covered by the node, right? And since we want to apply dynamics programming into this problem, it's very crucial for us to identify what would be the subproblem, right? So we have gone through this definition of the subproblems, which is as we have defined the SV0 and the SV1, right? For SV0, it indicates the size of the vertex cover in the subtree rooted as the node V, if V is covered. Right? And that's the indication, the meaning of the indication of zero mean. Right? For SV1, it means the size of the vertex cover in the tree rooted as the node V. But in this case, V is covered, right? So we have illustration examples with SV0 in this case equal to 2, SV1 equal to 1, right? And then after this definition or identification of the subproblems, we always start with what would be the simplest case or what is the base case. So we know that the leaf 0 as leaf 0 would be 1, or to be 0 as leaf 1 would be 1. And we also introduce the relationships, how we are going to solve the, the problem, use the subproblems, right? And, for the SV0, since in these cases, the node V is not covered, which indicating that we need to cover all these children, right? So we would have derived this equations, which is we have introduced the notations like the W1, W2, W3 is just the V's children. And we have the relationships of the equations, which is SV0 equal to S1, SW1, 1 SW2, 1 SW3, 1, right? I mean, we just sum this equation together. So this will derive the relationship between SV0. For SV1, in these cases, the node itself is already covered. It's already inside of the vertex cover. So which means that we really we can either cover or not cover these children, right? I mean, in these cases, we just take the means between, SW1, 0 and SW1, 1, right? And then the relationship between the SV1 would just be like 1 add on top of W1, W2, W3, right? So this would be the how we are going to derive the problem, utilize the subproblems, right? And then we will move on to talking about pseudocode. This would be exactly we are going to transfer the relationship we have discovered into the code, right? And here we start from the very beginning. We assume the tree itself is already ordered from root to leaf. And then we will have tables to remember, to keep record or put the results of the subproblems, right? And then we will have steps. We have a loop starting from the, the leaf to the root, okay? Right. We would have started from the leaf to the root, and then if the V is the leaf, we just put the previous conclusion as V0 equals 0, as V1 is 1. Then we will calculate, the subproblems where V is not like a leaf. All right, we just leverage the relationship we have already discovered. We initialize SV0 to be 0, SV1 to be 1. Then we loop over, the node V's children. We will just, for the case of SV0, we just add SW1, and for the SV1, we just calculating or first finding the minimum between SW0 and SW1, and adds on top of this SV1. Okay, that's it. So basically, this set of equations just describe transform what the conclusions or the rules we have discovered in the previous slides into code. All right. So this is what we have covered in the last lecture. Let's just briefly go through this. Now let's move on to talking about like as we said before in the last lecture, like after this kind of introduction about the dynamic, how we are going to apply dynamic programming to solve this vertex curve on the tree. Let's take like a deeper analysis about the running times, right? And we probably already identified there will be in these problems, there will be like 2 V sub problems, right? And you probably will identify to say, okay, since there's already 2 V problems, what's the running time to solve each of the sub problems? Turn out that it will be like it will run over time to solve all the sub problems, right? Why? Because like we will realize in order to solve each of the sub problem, we just like explore like all the children's ages, and turn out that every age just explore once. So this is like a tree with the node V. There will be V minus 1 ages, so there will be like a order of V time to solve all the sub problems. All right, are we all good about this? Okay. So so this would conclude or finish the like the problem how we are going to apply dynamic programming to solve the vertex curve on the tree. Right. Let's move on to the very last one, which is this is also like a most challenging one, which is called all pairs shortest passes. Right. So the all pairs shortest passes, the input would be like a directed weighted graph, and the goal would be we want to kind of have some pre-processed steps or procedures on the graph G, such that we could quickly answer the questions or the queries. For example, what would the minimum distance from V to W, right? And the V and W are the 2 nodes of the graph. And like this, if you encounter with the problems, you probably already come up with one solution or simple solutions, right? I mean, since just find the shortest path, why not just run Dijkstra's algorithm on unfit queries, right? And and assume that all the weights are non-negative, then the pre-processing time will be 0 since there's no pre-processing time. And the time to solve to finish the query, Q queries would be the order of Q times E times log V, right? And you probably already consider, can we do much better? So of course, there will be like simpler versions. It's like, like once we run algorithm, we have received queries of like a V and W, then we decided to run Dijkstra's algorithm, right? I mean, from the source V. So right now in these cases, we just store all the results from all the distance from the specific node to the rest of the nodes, right? Then next time, if we receive like similar queries of like what's the distance from V to other node, we really do not need to run Dijkstra's again, right? I mean, you can just utilize the algorithm or the result we have previously stored. Okay, that would be like a small improvement towards the Dijkstra's algorithm. And like this is one case, right? I mean, the previous we just have very little pre-processing time, right? And it will take us quite a lot of time to finish or generate the queries. This is one side or one extreme case, right? I mean, you could have another side, which is like we just pre-calculating every distance, the distance of every pairs from V to W, and then we just once we have this pre-calculated result, or once we have query, we just return the pre-calculated values, all right? I mean, this would be another extreme case. This is like we have a lot of time on the pre-processing, and we will have like the result to the queries in a very limited time or in a very fast time, right? And one of the applications of this problem would be calculating the dynamic of the graph. Like when we have an input of like an undirected weighted graph, the diameter of the graph is always defined to be the longest shortest path of the node, right? And one of the examples would be like this. You see like this would be like a graph, and you can see like a diameter would be the like the longest shortest path, all right? I mean, diameter would be the length between the two like a node shown or highlighted in blue colors. This would be the longest, the shortest path. Again, so now let's consider this is the problem. We also want to apply this into like a directed and weighted graph. Again, that the output would be like a distance, which we just know the distance VW, and it is the distance, shortest distance from V to W for all pairs of vertices. All right. And like solutions would be we just run single source shortest path once for every vertex in the graph. Then it will give us the result, right? I mean, this seems like a reasonable, but before we really dive deeper, let's take a deeper analysis about the problem we have, about the algorithm we have proposed. All right. So we just run like a single source passes once for every vertex in the graph, and then we assume that all the weights are positive. So let's consider what would be the running time. All right. So in the graph, in a sparse graph, we're like in the sparse graph, the number of edges is always order of v, right? Then the running time would be of this algorithm will take like v squares times log b, right? And it's turned out to be fairly good result. It's very good. It's like it's basically optimal, and I don't think we could do like a much better or significant much better. I mean, this is almost like the basic optimal, all right? Especially in a sparse graph. And how about when we consider like applying this on the unweighted graph? Like instead of run Dijkstra's algorithm, we can just run like a BFS, right? And this will give us the result of v times e plus v, right? For the dense graph, where e is almost like order of v squared, we will have like achieve like a result of v cubic. And in the sparse graph, where like the edges, the number of edges is on order of the vertex, we will have like a v squared, right? And for these cases, in the sparse graphs, this is almost very good. It's almost like optimal. I don't think we can do like a really complicated. We can come out with very complicated algorithms to achieve significantly better, right? So after this kind of analysis, maybe let's just focus on like whether we can do something different on a unweighted graph with a dense graph. All right. I mean, let's move on. Let's talk about let's focus on these specific cases. Right. And like as the topic we are talking about is about like dynamic programming. So we probably want to consider whether we are able to solve like this problem, leverage the dynamic programs. But really, before we dive and apply this dynamic programming, we probably already need to consider or identify the two key features associated with dynamic programming, which are optimal substructures and overlapping subproblems, which are introduced in the next lectures. All right. It turned out the result is like the shortest path definitely have optimal substructures. For example, like if the P is the shortest path from from U to V to W, then definitely the shortest path itself, the P will contains like the shortest path from V to W, from U to V, and then from V to W, right? These two like passes are also shortest paths from the node U to the node V, and starting from node V to node W, right? So these are already exhibit all like optimal substructures. And then let's consider like overlapping subproblems, right? Like many shortest path calculations really depends on the like same subpieces. For example, if we come to consider like we already know the shortest path from like a U to W, this will already be helpful for us to find like other short passes, right? As long as it contains U and V, right? So like after we have identified these two like key features inside of the problem, the really challenging or really core question for us to consider is what would be the right subproblems. Like we have gone through this many times, it's crucial for us to identify or formulate the proper right like subproblems. Once that's there, we can immediately start with like the procedures of dynamic programming. So what would be the right like subproblems? This may be like a really it's maybe a little bit challenging to consider. Like but once we identify this, you will find it's quite reasonable. It turned out that like the subproblem, the shortest path, like a subproblem of a shortest path, starting from V to W, actually is like the shortest path from V to W. We have a constraint saying like the path has to only utilize intermediate nodes in the set of P, right? That's the definition of like we just use as a VWP as the definition of subproblems. And it may sound like a little bit like confusion at the beginning, but let's work with the examples, right? So again, the definition would be SVWP would be like shortest path from V to W that's only utilize the nodes in P. Right? We could have 3 different type of like a P set. For example, P1 would be there's empty set, right? Which means that there will be no intermediate node in the shortest path that's from V to W. And P2 would be like we highlight the node of P2 to be like a green node, and P3 would just be like a purple node. Right? Let's calculating the SVWP accordingly. The first one like shown in red color is SVWP1. Since P1 itself is just an empty set, this indicating that the shortest path from V to W is definitely would be like the directed edge starting from V to W, if there exists such. Right, and in these cases, we're good. There exists a direct edge from V to W with a cost of 100. Right. Now we just put this into the result, which is SVWP1 would be equal to 100. Right. Now let's look at like a P2. P2 we will have like one node, and the shortest path from V to W across like P2 would be like in the blue edges. Right, these will have like 2 edges. Each of them will have a cost of 40. So together we will have like 80. This will be like the cost of this path. So SVWP2 would be 80. Right, let's move on. Same ideas. Like let's analyze this P3. In P3, there will be 2 nodes, which is highlighted in purple color. Like each of the edges would have a cost of 10. So together, the shortest path would have like 30, right? So this would kind of the definition of SVWP. The shortest path is specified by starting node and any node, but also specified by the set of vertex we allow the path to cross, right? And after we identify, okay, this will be like a sub-problems in these cases, we already can start with like a simplest cases, right? And the good news about this, this is called like a fraud washout algorithms. So the good part about the algorithm is that we have relatively simple like a smallest sub-problems or the base cases, right? The basic cases would be depends on the complexity of the node P, right? I mean, the simplest set or format of P would be just empty set, right? So SVW, the base case of this would be SW empty set. It's just exactly equal to the weight of the edges from V to W. So that would be the very base case, right? Now you probably already starting to consider like what would happen if we consider like how many different P we could have, because the P would just be like a set, like subset of nodes. It turned out it will be exponential possible like a number of like a set of nodes, right? And which indicating that it will be exponential number of sub-problems. And if we keep applying this, applying the algorithm on exponential number of sub-problems, our algorithm may be like fairly slow, right? And in Freud washout algorithms, we kind of restricted, we have restrictions about the problem P, right? And it turned out that we have like these are the definitions of the P that would be used in these algorithms. So we will have very basic cases, which would be P0, which is just empty set, right? I mean, this is the base cases. After that, we'll have like a P1. The P set 1 would be like node 1, right? And for the P2 set, which contains node 1 and 2. For P3, we just increase 1 and 2 by the third node, which is 3, right? Turn out that we are kind of the set of like a P that used in this algorithm is just to be like ordering of the nodes. Each time we have a new set of P, we just add a new node on top of the previous one. Right? We gradually increase the number the number of the nodes inside of the P, right? In the end, turn out we will have like a V plus like a N plus 1 set, right? I mean, here the N indicating the number of nodes, right? This would be the number of the vertex or the nodes. Right? This would be the definitions of the P that will be utilized in this algorithm, right? I guess maybe you might sound like this kind of I do not see the reason why why we are trying to define this. But no worries, let's just move on. We will have the concrete examples, right? I mean, to explain why this kind of definition are reasonable. Right? So let's consider that in the dynamic programming, once we have identified the subset problems, we have worked out the basic cases. Next thing we need to consider is how we are going to solve the problem using the subproblems, right, or substructures. So now let's take a look at how we are going to use the pre-calculating subproblems, or assume that we're already calculating SVW P7, right? So the P7, the P7, the set of P7 is included the node of 1 to 7. Right now, let's kind of ignore what is the exact node of 1, 2, 3, and 4, and 7, right? Let's really focus on how we are going to calculate SVWP8, right? So SVWP8 means what will be the shortest path from V to W, utilize node of P8, right? And that will be definition of this. And it turned out that the result of SVPW would have two possibilities. One would be a shortest path that's starting from V to W that utilize the intermediate code from P8 is exactly the shortest path. From V to W, utilize the intermediate node in P7, right? That would be one possibility, which means the new node of 8 does not appear in the shortest path. That is one possibility, right? In these cases, this will be the same result, which is here. However, there's another possibility, which means that the node 8 appeared in the shortest path from V to W. You only utilize node in the P8, right? And in this case, if the node 8 appeared in the shortest path, which means that shortest path could be divided into two parts, which is shortest path from node V to node 8, and the shortest path from node 8 to W, right? I mean, only utilize the intermediate node in P7, right? I mean, that is the relationship that we need to identify, right? So here it means, the SVWP8, the result of SVWP8 would be the minimum values between SVWP7 or SV8P7 plus S8WP7, right? I mean, these are the two possibilities that will give us, derive the relationships between, we can utilize this pre-calculated subproblem to derive the new result of SVWP8, right? I hope you're starting to grasp the ideas of why we are kind of define, our set of P in the ordering, in the increased ordering functions, right? Now let's come up with one of the examples. Let's see, we will have example with 5 nodes with index from 0 to 1, 2, or 3, 4. At the very beginning, we would have the tables represents the shortest path between each pairs, right? I mean, for example, in this case, the shortest path from 1 to 0 to 1 would be the order of 2, which is this passes, right? And we also add a 0 for the shortest path from itself. From 0 to 0, we also add the 0, which is the shortest path. This would be the initializations, which means that P would be empty set, right? The shortest path would just be exactly the 8 of widgets, if the weight of edges, if it exists one, right? Otherwise, we just put the infinity, right? I mean, this will seem straightforward definitions. Now let's move on to the interesting part, which means that the P itself is no longer empty. There's the one node in P, which means that now we want to update our shortest path table so that the shortest path could contain one actual node, which is node 0, right? In this case, some of the entries or the items should be reduced, right? For example, in this case, let's look at these items, which is what will be the shortest path from node 3 to node 1, right? Shortest path from node 3 to node 1. Previously, it is just infinity because there's no edges from node 3 to node 1. But if we are allowed to have like actual node of 0, we could come with these solutions, right? Maybe let me choose another different colors. This would be the possible solutions, right? Then we will have the weight of 3. And then we can also look at like a shortest path from node 3 to node 2, right? Previously, we the edges would be the direct edge from node 3 to node 2, which has like a weight of 3, right? But so far we are allowed it to have shortest path to contains like node 0, which means that we are kind of have a shortest path would be 2. We reduce this shortest path from 3 to 2, right? And we just keep updating this because now we allow the shortest path to contain actual node, which is 0, right? This finished the iterations of like a p equal to like a node of 0. Now let's move on. Let's add a new node into the set of p, right? Which means the shortest path from node v to node w could utilize intermediate node of 0 or 1, the node 0 or node 1, right? So let's consider these cases. So previously we have like for these cases, for example, this is the shortest path from node 0 to node 3. So previously there's no like solutions. Right now, if we utilize like node 1 and node 2, you will realize that we have like a possible edges, possible paths from node 0 across the node 1 and go to node 3, right? Another example would be like what's the shortest path from node 2 to node 3, okay? From node 2 to node 3, we are able to like across this, right? Would have like a new edges of 5. You can keep you can kind of get the sense, right? I mean, if we keep adding new nodes, we will be able to reduce some entries or some items in the path. Now we can continue to add on top of this. We have like a new node with node 2 added to the P, right? I mean, we can keep doing this to update the sum of the items. For example, the shortest path from 3 to 4, node 3 to node 4, like node 3 to node 4, what will be the shortest path? Node 3 to node 4, the shortest path would be this, right? Node 3 to node 4, the shortest path would be this one, right? Then we have edge of 4. Previously, the direct edge gave us 5. Now we would have like 3, right? Okay. And we keep applying this until we will have like a full result. Gradually, we will have like like our P set contains all the nodes, right? And keep applying this, we will have the final result. This will be the tables that each item will contain the shortest path from A to B, right? And this will be the like the relationship or the how we're going to utilize the sub problems to solve like the sub problems in the higher levels, all right? Okay, so this will be the ideas, like we have like Freud-Warsaw like algorithms. Now this will be like implementations or cycle code. Let's just look at this. Or just be like translations of the previous relationship we have discovered. So we have like an agency matrix, like we have like a dimension of 3, which is like all of them be the vertex, number of vertex. We're going to initialize each pair of the nodes for like the iteration of 0. When we're talking about iteration 0, so it means that we just consider P to contain the empty set, right? I mean, then like the empty set would be, like just put the age of VW into the S0 VW, right? And then we'll gradually increase the iterations from like a P set, the P to be P set 0, P1, P2, P4, right? And each of them, let's consider what's this 4 lines of code. So the current iterations or current weights are from V to W, we just record this to say like a current D, right? I mean, then we compare what will be the cost from V to K. K is the new node added into the set, right? What will be the key, or what will be the cost from V to K, and then K to W, right? And we are able to identify, add these 2 items together to see like compare with the previous one. Let's see like which would be the minimum one. Then we just put it in the new iteration of K plus 1, right? I mean, that would be exactly the equations we have been talking about, right? I mean, this is just the same of formulations or implementations of these equations, right? But after looking at this, you probably already identify. Probably we do not need to keep like order of 3 to remember this. So that's why we will have the simpler versions, because it seems like each iterations the only thing we need to utilize is the previous, the result, right? We don't really care about the first iteration or second iterations. When we're doing k+1, we only use the result of k, right? Then we started to optimize to thinking we really do not need to utilize the like a 3-dimensional array to keep record, right? What we could do, we just simplify this. We just use like a 2-dimension arrays here. Then everything would become simplified, right? We just calculate the minimal result and put this in the SVW, right? We can keep simplify this. This is simplification, just one line of code, which is quite elegant. Okay, let's after we have finished about the introduction and about how to apply this dynamics programming into solve this problem, let's consider, as we usually do, let's see what will be the running time, right? I don't think we have enough time for you to give this answer, so I'll just directly put it. You probably already guessed the answer, right? The complexity would be, the running time would be v squared, v cubic, right? If you compare these cases with the previous result, if we run Dijkstra's algorithm, we just run like a previous like a BFS, we kind of reach the same densities, the same like complexities, right? But like this is simpler to implement, like also implementations, right? I mean, do not need to really have like a large like a storage. This is some kind of good about like this Freud and Warsaw algorithms, right? And remember, the key ideas or the key crucial one is when you're applying the dynamic program to solve a specific problem is identify the subproblems. Once that is there, work on the simplest case and starting to see whether you can utilize the result of previous subproblem to solve the current subproblem, right? All right, so let's move on talking about some of the variants. This would be one of variants would be path reconstruction. It means that we actually not really care about like the path. We care the cost or the width of along the path. We actually want to have a way to return the actual path from V to W, and how we're going to represent it sufficiently. So I just leave this for you to consider. And another case, another variance of this algorithm would be called transitive like closures, which means that we want to return or come up with like a matrix where VW equal to 1 if there's a path from V to W. Otherwise, it would be 0. How we're going to utilize this like algorithm to generate this matrix, right? Again, I just leave this for you to consider. So that would finish like the whole topic, the whole materials related with dynamic programming, right? Again, the dynamic programming is like you identify the suboptimal optimal substructures and trying to find what would be the overlapping subproblems. Identify the definition of subproblems, work on the simple case, derive the equations, how to utilize like a pre-existing or pre-calculating the subproblem to solve like a new subproblem at like a higher levels, right? And keep applying this, you're going to solve these problems, right? So good. We just finished with the dynamic programming. Do we already all good about this? Do we have any questions? No? Okay. The end. So it's kind of exciting. So let's consider, first of all, we would like to thank all the tutors for their hard work. Like which this is making this courses to be like a very useful and interesting. Then let's move on to today's plans. We will have several announcements. It's always related with the final exams, which you really care about. And we're talking about what will become next, and we will have some algorithm tips, and we just wrap up, right? So announcement always is first one is finals. The finals will held as like a Friday, which is May 3rd. From the time will be 2:30 to 4:30, and the location would be MPSA 1A and 1B, right? And the format mostly will be multiple choices. And what you can most important thing you need to consider is what to bring to the quiz, right? The first thing is one double-sided sheet of paper with any note you like. And your pens or pencils. Remember that you may not use anything else, no calculators, no phones, etc. And questions will be cover like topics from all lectures, but we'll focus mostly on like topics after the post midterms. Right? So that's this one. Now we also have some survey invitations on like AI like a program tutoring systems for data structures. So the goal would be measure, like the efficiency of AI powered like tutoring systems to prove students' learning outcomes of data structures, right? And the task would be solve the data structure programming task with AI tutoring systems. So duration will be 2 hours. When you do this, you get a reward for like 20 Singapore dollars and actual consultation for data structure problems. You can, if you're interested, I just leave this like a QR code here. All right. I just pause for a while. Okay. Okay, I need to move on. So you probably want to take pictures on, after we release the Zoom, right? Also about the problem set, I think you already received the announcement, like deadline for submission all assignment, including the lecture reviews and the optimal practice is end of week like 30th, right? Which means you have to do this until Saturday, like April 27th, right? And then there's another exciting news, which is like the tech interview preparations for summer. So the SOC will be conducting like a 10 weeks program this summer to ensure that all our freshmen are well prepared to handle all, like all technical coding interviews when you're applying for technical internships, right? And this program will be taught by like senior students with like a wide range of internship experiences, for example, in several companies like ByteDance or like Jupyter Labs, something like that. And like there will be like a program outcomes. And also, if you are interested in, we will just have like sign up forms in the cosmology. So just wait, I'll just let you know here, right? So this will be super useful, I think. Okay, then we're talking about what will become the next one. So the next one would be, like why this is courses, like what's the importance of these courses. As I said at the very beginning, like algorithms are everywhere. So it's very important for us to know these algorithms, and this algorithm play a crucial role in the world we are living today, right? As the examples, like when we type the Google things, we will trigger a bunch of algorithms, including the internet algorithms, databases, web servers, etc. So it's very important for me to get familiar with this like algorithms here, right? And also, like this would be like our course. What is the structures of these courses? Let's look at these cases. Let's have like a brief summary about what I have gone through this semesters. So we always start with some like a series at the very beginning. Then we'll move on to talking about the searchings, sortings, like searching trees and hash tables, etc. Then we move on to like introduction about graphs, searching on the graphs, and also like a single source shortest path or topological sorting, single source shortest path into minimum spanning trees, right? This will be the procedures. But the most important part in the courses of algorithm data structures, we hope you to focus on the problem solving, right? We hope you to grab this, develop this ability to utilize the algorithm data structure to solve problems, right? That will be the key part. And also, like when you design, when you kind of choose your right algorithm for the right problems, when you really encounter like real world problems. And when you design new algorithm for new problems, you already maybe consider with this keyword, this trade-off, right? And you probably want to trade off between like a computational cost or like a storage or like something else, right? I hope you get the idea. This kind of idea of the trade-off may recur again. And what comes next? So far, we have talked about like several important topics, like for example, the binary search, like along with this binary search would be an important concept, which is optimizations. Like the optimization has played like a wide range of roles in various generic problems, especially in the like a community of machine learning. Like this like stochastic gradient descent is one of the widely used algorithm that has become the foundation to how to train these neural network models, right? And also we're also talking about the sortings, like we have talked about some key properties about the running times and the space usage. The next thing you probably want to consider is what would be the sort of faster way, how we're going to sort this faster and faster. And these turn out there's keeps increasing in these areas. You probably also want to utilize, pay more attention to this. We're also talking about searching trees. And one of the key problems in the tree related question would be how we're going to store, index, or searching with high dimensional data. So that is also important. We're also talking about hash tables, we probably want to come up with like a better collision solutions or like a more realistic hash-link functions, right? And we're also talking about shortest path and also like minimum spanning trees. All of this will become like related topics with big data, right? And we probably already realized we're already in the age of like large models, especially large language models, there's a large vision model, etc. And how we're going to represent the training and maintaining these models also associated with big data and parallelisms and distributed network applications. All right, these are something that you probably want to continue to explore if you're interested in. Specifically, if you are interested in the modules, for the algorithm modules, we also offer like CS3230, which is the design analysis of the algorithms. We also, for the series, also provided with a series of computations. In terms of the software engineering modules, we provide the software engineering, which is CS2003, and we also provide system design and programming modules. And what will be the next one? It really depends on which area or direction you want to go, right? We have distributed systems, game design, computer graphics, machine learning, computational biologies, and etc. And also, you probably want to see, like, I'm interested into research, all right? And we also several opportunities. We have UROP, which is undergrad research opportunities. We have Turing programs. We also have, the FYP, final year research project, okay? Feel free to reach out. Okay, there's also several research, like algorithm tips, we want to share with you. The first one would be always try some small examples when you're trying to, design or working with a problem, you don't know how to do this. Maybe always trying with small examples. They will help you to understand the structures, right? The seventh one would be, start with like naive solutions. Don't worry, it's okay for you to come up with naive solutions because this simple algorithm are useful, but it also become like a baseline for you to develop more complicated algorithms. And also we will try special cases. For example, in the special case, if you look at the problem for an hour, you don't know how to solve it, you probably want to simplify and try smaller cases. This will also help you to have a better understanding about the algorithm, about the problem itself. And also, you probably have it'd be great to have like ideas about how good is good, or what will be the target for, or what will be the natural lower bound, right? And the fourth one is about the metrics. Like a matrix kind of provides like a way for you to evaluate how good the algorithm are right now. And also find the invariance. This is also important because you will be able to find the problems requires and what does the algorithm guarantees, right? Maybe make a guess. What will be the second one? Would be try binaries? Like this kind of straightforward, quite surprising, but it's very useful. You may, many algorithms could just be optimized using binary search. The very last one, let's make a guess. What do you think would be the most important tips we recommend? Divide and conquer. All right. This would be like trying to consider like divide and conquer, looking for sub problems and structures, right? So these are the several useful tips that we share with you. In the end, okay, the goal of this courses is trying to apply algorithmic thinkings and techniques and describe the structures and operations of different data structures, and also access the suitability of different data structures and algorithms, and trying to adapt to existing data structure and algorithms. All right. So this means the end of these lectures. We hope everyone has fun. If you want to ever continue to check about algorithms, feel free to drop our office. Remember, our door of office is always open, right? So great, it's over. Congratulations, everyone. It's very excited for us to walk you through these journeys about the data structure and algorithm, right? That's it. Thank you so much.